All right, let's continue finding derivatives of exponential functions. Okay, we left off with example 2. Let's find dy dx if y equals that mess. Oh my gosh, imagine trying to do that with the limit definition, right? We're just going to use all kinds of properties that we've developed because I see e to a power of stuff, so that's a chain rule. I see square root of stuff, so that's another separate chain rule, and all of this is happening inside of a product rule, right? We've got two separate functions multiplying together. So we're going to do a very interesting derivative right here, and just don't lose track of where we come from, right? What does a derivative do? It finds the instantaneous rate of change of this function. It finds the slope of the tangent line and all of that good stuff. So let's go ahead and do this. And again, there's a whole lot of different stuff going on here, but I'm kind of just going to say each piece very specifically as we work out the product rule and then the chain rule and all of the rules that we're using. So let's go ahead and dive right in. Dy dx equals, so this is a product rule first and foremost. Okay, product rule first. Okay, so we've got this part is the front, or the first and the second, okay? So it's probably a good idea to think of that 5x plus 2. That's actually 5x plus 2 to the 1/2. Okay, think about radicals in terms of exponents so that you can use the power rule when we get to that part. Okay, so here we go. Let's use the product rule. So the product rule says first times the derivative of the second plus the second times the derivative of the first. So let's go through and work it out. So for the first, just leave everything alone, e to the x squared plus 1. So that's the first, times the derivative of the second. So here we go. This is going to be a chain rule. Okay, so stuff raised to the 1/2 power. The power rule on the outside says 1/2 times the stuff, reduce the power by 1, so that's going to be negative 1/2. And then don't forget the chain rule, times the derivative of the stuff. So the derivative of the inside part is 5. Okay? Halfway there. So that's the first times the derivative of the second plus the second. And let's go ahead and write that as 5x plus 2 to the 1/2. Okay? Times the derivative of the first. Okay, so be careful. The derivative of e to the u, or e to the stuff, is itself, times the derivative of the stuff. So the derivative of x squared plus 1 is 2x. All right, and that's all of the pieces. Now is the algebra part, okay? We're done with the calculus for this problem. Now it's all about the algebra to try to clean this up. Okay, so a lot of different stuff that we can do. Let's think about this. Excuse me. So like we did in chapter R, we did some factoring practice. So let's look at this and see if there's any meaningful, useful things that we can factor out. So just looking through all of this, it looks like perhaps we could factor out. Remember, there was a technique where we would factor out the lowest power or the smallest exponent of the term there. So the 5x plus 2 to the negative 1/2, that can be factored out. Okay, and that's going to be a little bit strange, and we'll definitely pay close attention. But there's some other stuff that we can factor out too. I'm also noticing this e to the x squared plus 1 is a common factor. Okay, so let's be careful, and I'll explain each piece as we're going. I'm factoring out a GCF of the e to the x squared plus 1, which is a part of both of these terms. Okay, so e to the x squared plus 1. I'm factoring that out. Okay, I'm also going to do a technique where I factor out 5x plus 2 to the negative 1/2. Okay, and we did a couple of examples like this back in chapter R, where we factored out the part that had the smallest exponent on it. Okay, so let's go through and be very careful about what this is actually going to do. So looking at this whole first section here, we removed the e to the x squared plus 1. There's still this 1/2 there, and there's still this 5 there, but we also removed or factored out. Remember, factoring out is like dividing. So we removed the 5x plus 2 to the negative 1/2. So the only thing that's left is this 5 times 1/2. So let's just write that as like 5 over 2. Okay? Plus. Now, we removed the e to the x squared plus 1. So all of that is gone. But then how do we deal with factoring out 5x plus 2 to the negative 1/2 from the 5x plus 2 to the 1/2? So that's a little bit weird. And like I said, we did an example in the past, but let's go ahead and think about the scratch work there. Remember that factoring out a GCF is the same as dividing. So what would happen if we did 5x plus 2 to the 1/2 and we divide by 5x plus 2 to the negative 1/2? What's the result? Okay, that's what I'm getting at. Now remember that if you've got an expression divided by an expression, the powers subtract. Okay, that's the power, the subtraction rule if you do a quotient. So if we have 5x plus 2 as the base, it's going to be top power minus bottom power. And so those add, and so we end up with 5x plus 2, and then that ends up being plus. So 1/2 plus 1/2 is 1. That's really nice. So that 5x plus 2 to the 1/2 actually becomes 5x plus 2, just without an exponent on it. Okay, there's still that 2x that's right there though. So times 2x. Okay, so that cleans up the expression a lot because now we can go through and actually try to combine some like terms a little bit on the inside. So let's continue. There's lots of different ways to simplify this. This is one of the options, but there's other options for how to eventually get to the same final answer. So let's think about this. Let's go ahead and say, I just want to kind of choose the path of least resistance here. Let's see. Yeah, okay, so I'm thinking this negative exponent part can go on the bottom, and so we can write this as e to the x squared plus 1 times 5 over, let's actually do a common denominator here. Lots of different ways to do this, but I want to just kind of think about a common denominator right there, okay, to try to combine the stuff that's in there. So 5 over 2, if I want to add, let's multiply the top and the bottom of this by 2. Okay, so we would have, let's see, this 2 and that 2x would turn into 4x. So we would have 5 plus 4x times this 5x plus 2. And on the denominators, common denominator is a 2. Okay, and all over, because I'm putting this 5x plus 2 to the negative 1/2, I'm putting that on the bottom. So 5x plus 2, and it's going to be to the positive 1/2 down there. Okay, and then finally, fractions on top of fractions are not all that nice, so we typically like to clear all of the fractions if possible. So that 2 right there, let's multiply the top and the bottom by a 2. And so that would actually just multiply this e to the x squared plus 1 it would distribute into these brackets. So we don't need to distribute the 2 onto both of these pieces because there's not actually distributing happening. It's just multiplication. So that can just fully cancel. And then this 2 multiplies into the bottom. And then we'll have our final answer. That's probably the nicest final answer that we can have, where if I canceled out that 2, I'm kind of doing a couple steps at once. Let's see right here. How about 4x times that 5x? So let's write this as e to the x squared plus 1 times, okay, and then in here that 2 is canceled. I've got 20x squared 20x squared plus 8x, and then there's that plus 5. All over, and this 2 distributes onto the bottom, and then I'll go ahead and switch that 1/2 power. Let's switch it back to a radical and put the 2 in the front. Why not? So that's 5x plus 2. And there we go. That's probably the nicest, cleanest, best looking final answer that we can get. Okay, so like I said, the algebra was probably the hardest part of that entire thing, which is definitely why I wanted to do some practice at the beginning of the semester so that this doesn't blow your mind too much, because yeah, the algebra is usually the hardest part. All right, but yeah, that's a good one. That's a really good one. Okay, example 3, and then I'll make a separate video when we talk about the logistic function. So in example 3, the amount in grams of a sample of uranium-239 after T years is given by that function, okay? So amount in terms of T. Find the rate of change of the amount present after 3 years. All right, so like I said in the past, anytime we see this expression, rate of change, that means derivative. Okay, that means instantaneous rate of change. Okay, so we're gonna find the derivative of this, and then after 3 years, we just want it at a specific moment. So we're gonna find the derivative and then plug in 3 to the derivative, and that's it. Okay, so let's go ahead and do it. A prime of t. So we've got 100 times e to the stuff. Okay, so there will be a chain rule here. So remember, a constant times a function, the constant just keeps multiplying along. Okay, the derivative of e to the stuff is itself. So don't forget, you have to include all of the stuff times the derivative of the stuff. So the derivative of negative 0.362t with respect to t is just the constant part. Remember that the derivative of a constant times the variable, if you reduce the power by 1, it becomes a 0 on the power, which makes the variable turn into a 1. Okay, so it's times negative 0.362, just the constant. Okay, and then we can clean that up just a little bit. I think this one is a lot easier than the previous one. It was just kind of to see an application here. So let's multiply the 100 times the negative 0.362. And so we get negative 36.2 e to the negative 0.362 t. So that's the derivative, and it's very powerful because now we can find the rate of change at any moment. So they wanted 3 years, so that just means we find a prime of 3, and so we're plugging in 3 into the derivative. Okay, plugging in 3 for t. Okay, be careful how you type this into the calculator. I recommend as you're typing this in, use extra parentheses around the whole top so that the calculator knows that you want all of that product is the power of e. So negative 36.2 times e raised to the parentheses, negative 0.362 times 3, close parentheses, and we got negative 12 point, several decimal places, 12.219. How about negative 12.22? Okay, now what did we just find? Make sure you understand the units here and why is this negative? Okay, so remember when we were talking about like decay of this, so that makes sense. So I'm thinking about this negative number, it means decay, right? If you've got a radioactive half-life type of situation, then you would have like a decay happening, okay? And so what this means is the rate of change of the amount present after 3 years. So this is negative 12.22, and this would be, what's the units? Grams per year. So what this means is the mass is reducing at a rate of negative 12.22 grams per year after 3 years. That's the instantaneous rate of change. Okay, and it makes sense that this is a negative number here because this is like exponential decay. All right, so I'll make a separate video to pick up on the logistic function. All right, so stick around for that.